Hi there, thank you to everyone for joining me for this presentation today. Good morning, good afternoon, good evening, wherever you are in the world and at whatever time you are watching this. I'm excited to be here today to talk to you about building and deploying AI-based machine vision systems. Now, deep learning is so prolific in our lives, it's almost unnecessary to introduce it as a concept. We see it daily, or at least it sees us, whether that's with content suggestion on streaming services, fraud detection in our banking transactions, speech recognition on our smartphones, or cheating on our homework with ChatGPT. It's now very rare also to not see deep learning offered in machine vision systems, as it's so powerful in what it can now achieve. Many of the elements of deploying a machine vision solution based on deep learning are the same or similar to those using traditional rules-based processing. However, the data element of deep learning brings new challenges. So today I would like to provide some ideas on how to achieve the best results in deep learning based projects, broadly based on the concept known as machine learning operations, or MLOps. MLOps was originally conceived to make a link between data scientists and deployed systems. It combines the best practices of machine learning, DevOps, and data engineering to ensure robust, scalable, and efficient deployment and management of machine learning models. From a machine vision perspective, the products available on the market somewhat remove the need for data scientists and the additional tools and puts the process in the hands of us as machine vision engineers. However, we can still use and very much benefit from the principles. Designing, building and deploying systems based on deep learning is unlikely to be and really should not be a simple linear development. Rather, it is an iterative approach where lessons and experience from each stage can and should be fed back into earlier stages to refine the process and finish with an optimized system or a continually optimized system. We start by scoping out the project, then move to the data collection, the model building, the deployment, and what we can call the monitoring stage or continuous integration. At each stage, we might gain some insights or spot previously unforeseen challenges, which means we might need to change something in the previous step or an earlier step to improve the system. For example, during the data acquisition stage, if the application is for detecting defects in a product, we might find that we don't see certain defects very often, so it's challenging to acquire the data for this and build a reliable model, and this might change the scope of the project or the timelines. Obviously, we want to mitigate against this as much as possible during the designing and scoping stage, but things often come out in later stages that were not considered, so making adjustments on the fly and as early as possible is a great approach. For context, I would like to briefly introduce two products from IDS, which I will refer to during the next 20 minutes. IDS NXT is our user-friendly AI-based all-in-one vision system where we provide the camera and the processing hardware in the NXT Malibu, Rio and Rome cameras, as well as a versatile software environment for acquiring image data, annotating the images, training neural networks and creating apps for evaluation and actually running the applications. DenkNet offers the ability to solve highly complex tasks with a simple implementation of annotating image data and training models. We can work with fewer images. There are some really nice tools for faster annotations, and a solution based on DenkNet is based on a PC, so it means that we can scale the processing to whatever the application calls for. So with that, let's step into the process of MLOps. The first step is designing or scoping out the project. Firstly, we need to ask, is it truly an AI or deep learning task? Whilst AI and deep learning is popular and very much a buzz term, we need to consider whether traditional image processing could actually still be the best option. So we ask, what do we need to do? Do we want to detect something such as defects on a product, count objects that might appear randomly, locate or identify something, or maybe we want to read challenging characters for an OCR application? The rule of thumb is if it's something that a human would be able to detect by eye and it's variable in nature, it is a very good candidate for deep learning. If we need quantitative measurements, such as measuring the diameter of a can to micron accuracy, this is unlikely to be an AI task and is best served with rules-based algorithms. Once we've defined the task, we need to define metrics. There's lots of things we might want to consider here, but typical requirements would be how many parts per minute or per second do we need to inspect? Or what is the minimum target quality score for a positive detection of an object? Now here the answer may be difficult to fully define at this stage. However, if it's a quality process like these nuts in chocolate, maybe we can accept 80 or 85% as an acceptable score for a positive detection. If it's a more safety critical check, perhaps for a seatbelt manufacturer or smoke alarm manufacturer, we'd want to be at 99% or likely higher. And with respect to reject mechanisms for a manufacturing line, or sounding an alarm, or activating a cutout on a health and safety system, how quickly do we need a result for a system to operate effectively? Then, having considered the metrics, this feeds through to the resources. We can ask what will be the best processing method to achieve our goal. Do we need real-time results? This is typical for inline quality control processing or health and safety systems, such as those examples given before. Or could we benefit from batch processing, typically used for non-time critical applications, such as medical diagnostics? This also tends to lead us towards whether we need to use edge or cloud-based processing. Edge-based processing gives us the advantage of speed, of security of data, since no images need to leave the site or even the camera, and anonymity as well in some cases. Cloud processing has other advantages in that it is generally more easily scalable and there's no requirement to maintain the processing platform. And any server upgrades that come from our service provider could mean an improvement in performance without having to do anything. But realistically, for our typical applications, edge processing is the most likely target, in which case we also need to think about the target hardware. Do we need to deploy on a compact or an embedded PC? Can we use an industrial or desktop PC and select the GPUs or CPUs necessary for the desired performance? We can look at benchmark figures to give us some indication of what would be necessary. And with the NXT, we have a known processing target, so we can be specific about the hardware requirements even at this early stage. And we might also want to consider how our system will interact with a wider system. Do we need simple digital I/O lines, a PLC interface, or some other comms interface? Then, having considered the hardware elements, we also need to think about the human resources. Acquiring images for a deep learning based system can be really time consuming and should not be overlooked. It might not be human intensive, but it could take a long time still to accrue enough images for the application. Once the images are available, they then need to be labelled. In some cases, this is an entirely manual process, which can take a long time to complete. The good news is that there are ways to accelerate this, and we will see an example later on. And once we have the working system in the lab, there may still be significant effort to install the system into the end customer's facility. There are no simple answers to the time involved. This knowledge just comes with experience, but definitely shouldn't be underestimated. The last section here is a proof of concept, and we can consider this to be like a mini MLOps project itself. First, we look to scope out what we want to achieve as part of the proof of concept. The advice is to start simple. So, for example, if the end system requirement is to inspect a product with 5 different potential defect types, we might pick just one defect to start with, and this could be the one that is the most common and causes the most pain. Or maybe we pick the most challenging defect to detect to give us and any stakeholders confidence in the approach. We need to collect some images to work with if we don't already have some, and the platform used depends on what that number of images might be. It could be 50 to 100 per class or defect type in some cases. And this can often be a stumbling block for even the proof of concept phase. Fortunately, there is an answer, since with DenkNet we can run a reliable proof of concept with as few as 10 or 15 images per class. We need to annotate the images, and then we need to build a test model in order to test some of the agreed process. Now, both our NXT solution and DenkNet software provides the means to test this without any, or at least very minimal, software development. DenkNet through the cloud-based AI Hub, and NXT through the cloud-based Lighthouse, where we also have a rapid low-code development tool that allows the user to put together a custom app that can then be run on the camera. And at this stage, we can gain a good indication of the potential success of the project and the approach. And this is always good to present to stakeholders at an early stage to gain approval for the rest of the project. After we have a successful proof of concept, we can start to work on the main project. The next step in our process is around the data, and this is perhaps the most significant element of the MLOps process. In the past, deep learning-based systems have been very much model-centric, and this means we would acquire some images, perhaps without too much consideration, and then work hard on the model to find a working solution, and this required deep learning experts, our data scientists. More recently, there has been a drive towards data-centric AI, where our focus is on acquiring good quality data in order to achieve the best results. The steps we see here are supporting this data-centric approach. We will achieve better results if we agree a set of rules of how we will acquire the data. For example, what will be in the image. If we consider a person detection application, and here we see our lovely data scientists again, do we want images of just heads, head and shoulders, or do we need to include the full bodies? The application will likely dictate what is required, but it makes sense to be clear at this stage rather than later end up with half data that we can't use or that we have to manipulate to our purposes, or even acquire more data. We also need to consider any variations that will be present in the application and ensure that our training data includes these variations. We can see here a video of the different training images for our example Lego gear detector, where we see a variation in brightness and backgrounds in order to deal with the variations the application will actually see. How many variations you need to deal with will be very much dependent on the application. It could be purely related to product variations and everything else is fixed and constant. But at the extreme end, there could be an incredible amount of noise that we need to consider in the image data. Consider self-driving cars and the sheer variety of things in the scene. The application would be primarily detecting cars, other road users, the road itself, pedestrians and some road signs. But there will be other irrelevant signs, there will be buildings, there will be street furniture, trees, bushes, as well as any variations that different weather types can introduce. So we need to make sure that it's all represented in our data sets and to have an idea of it at the start. Once we have set the rules around the images, we can start to collect the image data based on these rules. If it's at all possible, the images should be taken using the same camera and in the same position as the final installation. Now, this is not always a realistic demand if the system is still to be built. It is still possible to use existing data at this stage, as we might have done with the proof of concept, but better results will come from datasets that are entirely representative of the end deployment. Once we have collected our data, the next thing we need to consider is the annotation of the data. One of the key principles here is consistency. If we take the example of the Lego gear detector again, we might define that the bounding boxes are drawn around the gears tight to the edge of the parts. So we'd want to be consistent in how the bounding boxes are drawn to get the best results. This is of particular importance if we have multiple people annotating the data. We also need to consider how we will deal with things like occlusions. Again, looking at the gears, we might decide to draw bounding boxes around only the visible area of the gear, or we might decide to draw the bounding box around where we expect the entire gear to be. Either approach is fine and will likely be dictated by the application, but the key once again is consistency. Now, as a side note, the process of annotating data can be extremely time consuming and also tedious. More and more we are seeing tools that accelerate this process. For example, in DenkNet, we have a one-click annotation tool which runs a pre-trained network to gain some idea of how to segment the parts in the image. And then, as an annotator, we simply just need to click on the item we want to label and the bounding box is automatically applied. This also works with segmentation, where we're looking at pixel accurate annotations, and it's possible to deal with overlapping parts also with an additional click or two. Now, having experienced manually labeling images, I can say from personal experience that this really is a massive benefit. Next, organisation. It really pays to have good organisation of the training data. We should have consistent labelling of images as well as consistent annotation names. For the latter, if we have multiple data sets that have the same class in that we want to use, we need to ensure that the same class in dataset 1 and dataset 2 are both labelled the same. Otherwise, we may end up training two classes of the same thing as different things and degrading the performance. It's an extremely good idea also to include some notes about the dataset, who created it, when, what it is, and any comments. As we're working with an iterative approach in the MLOps model, it's highly likely that we will come back and look at these data sets in a few months' time, possibly a year, and trying to remember what each data set consisted of is really challenging. Therefore, notes are a very useful prompt. Likewise, we want to be sure that our file structure is also well planned and uses good, understandable naming conventions if we are storing the data locally. We often use data augmentation to increase the number of samples that we train from and build in more synthetic variations. With our NXT software, we can manually select the augmentations we want to include. This could be image flipping, distortions and translations, and brightness and color variations. Here we need to be sure that we only build in variations that are natural to the application. For example, if we were looking to detect the IDS logo, it would not make sense to perform a left-right mirror flip on our training data if this was a scenario that we would never see in the application. The final point here is that we need to ensure that we have a test data set, and this should conform to all of the previous rules and guidelines we have set, and we should ensure that as many of the products or ambient variations are present in the test data set. This dataset should be kept totally separate from the training data so that then when we are testing, we are certain that we are only taking results from brand new image data. So getting the data element right at this stage makes the later steps much, much easier. Turning to the model training. When it comes to building the model, we have only to select the model type and experiment with the results. The model selection will largely be determined already during the design stage. The most common methods are image classification, which provides a classification result for an entire image, object detection, which finds trained objects that appear randomly in the scene and predicts a bounding box. We then have segmentation, which will determine which pixels in an image belong to which trained classes, but that doesn't separate overlapping instances. So then we have also instance segmentation, which goes one step further and will differentiate between instances in the same class. We have anomaly detection, which detects deviations from the norm in an image and is trained using only good or okay images. And OCR, where with DankNet we can read characters based on a pre-trained model and then refine the model for a specific application. And for DankNet, this is the only decision we really need to make. The rest of the model selection process is handled automatically and will be intelligently selected based on the image data and the annotations provided. With NXT, as we have this known platform that the model will be deployed to, with classification and anomaly detection, we can decide what our decision time will be and can therefore target the defined response time from our scoping stage. Now, there may be some trade-off in performance against the processing time, but that's something that we just have to balance as a system developer. With the model trained, then both NXT and DankNet provide a graphical feedback on the training success, so you can see how well the model has trained. DankNet even provides an early candidate model or early candidate models to test with whilst the training continues, so you can get an early indication of how well the model will perform even before the training is complete. And the Quality Center allows the user to dig further into the results. With NXT, we can see a confusion matrix which plots annotations against predictions and then highlights areas where there may be some issues. And we can also test the processing performance on our hardware platforms by exporting models from the cloud-based environment and test on the target hardware. With the NXT, this will be our camera, and with DankNet, there is an offline analyzer utility which allows us to test the processing time on our CPU or GPU processors. And then linking back to our iterative MLOps model, anytime we find low performance or issues, we can revert back to image data, to models, and refine any elements here. Maybe it is the image set itself and we find we need more examples of a particular defect, or maybe it can highlight issues with the annotations or labels. The guide here then is to correct these issues and repeat the model stage until we are happy with the results. Once we are happy with the model that we have built and it's running in the lab, we need to think about then deploying the system. When it comes to deploying the system, if we haven't already pinned down the processing hardware and the interfacing, we would need to do this and, of course, develop any software and test the solution before deploying to site. When we come to deploy the system, there are a number of ways that this can be done. If we have an existing inspection system, whether that's automated or human inspection, we can deploy a shadow system where our deep learning system is not making critical decisions, but only accruing results and statistics that we can then compare with any existing quality control process. We might also use this opportunity to acquire more images for training purposes, especially to capture images of the more infrequent defects or occurrences. Once the performance is at a sufficient level, we can turn the system on completely or move to another deployment method. Another way to work is the canary method, where here we might divert, say, 10% of the product or decision process through our new deep learning system until the required performance is proven. If problems are detected and we need to go back to an earlier stage of our MLOps process to refine things, perhaps the confidence score produced is below an acceptable level, for example, we haven't committed 100% of the product to the inspection and accrued a whole load of false defects, or worse, passed lots of defective product. We could also use an A/B deployment method where the existing quality control process or system stays active alongside the new deep learning based system, and we can switch between the two. Again, should problems be identified with the new deep learning system, we can switch back to the original process whilst the issues are addressed. The key thing is that if we are replacing an existing system, we have a fallback plan should the performance not be where we expect. The final piece of our MLOps model is very important, and this is the monitoring the system over the time. Firstly, if we are collecting lots of statistics, we can check the general system performance. Is the reject rate creeping up or down unexpectedly? Is the system starting to run hotter, or the CPU load slowly creeping up? Are the metrics for the vision side of things changing over time? For example, is the average pass score changing? With this, we can check for any changes in the performance of our system. Some may not be related to the deep learning element of our system, but by monitoring all elements, we can be alerted to changes in the system. And this may be through data drift, where the image data starts to change for some reason, or concept drift, where there may be a change in the expected or the intended results. There are things that might change as part of the process that affects the appearance of what we are inspecting. If we have a line producing bagels and there's a change in the appearance, perhaps due to a process change or an ingredient change, we need to be alerted to this, and this may lead to us going back to the data stage and acquiring and annotating more images for this new appearance, either to be able to reject it or accept it if it is indeed acceptable for the producer. When we consider face recognition, going back 4 years, face recognition algorithms were based on the full face. But when we were hit with COVID, suddenly everyone in public was wearing face masks. And this variation that previously was not included in the data set needed to be added in. Or maybe there could be seasonal variations to products that were not available when the original system was deployed. Some early crops of vegetables, for example, have a differing appearance to late crops. If we do not have access to images of the later crop for training purposes, we might start rejecting perfectly good products. So we would need to retrain this model based on the new data. All of these examples of data creep need to be identified and addressed. So it's important, therefore, to keep reviewing any deployed system to ensure that external factors are not affecting the performance. Anything then detected can be taken back to earlier stages of the MLOps model to refine and to improve and to optimize our system. So I hope I've been able to illustrate the benefits of the MLOps process, especially the iterative nature of it, that we can really benefit from having this data-centric approach with a strong focus on the images, having consistency in images and annotations and a good structure of our data. And we can start with small proofs of concept to gain confidence at an early stage and learn some important early lessons. And finally, monitoring the deployed system to identify issues that can be corrected. Thank you very much.